Hi, Dr. Huan here. In this section, we begin with a review of inverse functions, their definition, and when they exist, how to graph them, and how to find them. And after that, we'll investigate the relationship between the derivative of a function and the derivative of its inverse function. So now let's begin with a quick review here. So we have a simple function f of x equals x plus 3, and we have a restricted domain. We only consider these four values in set A. And then, so now B is the image of this guy. So when x is 1, the value is 4. When x is 2, the value is 5. When x is 3, 6. When x is 4, 7, right? So basically, this graph represents the function f. 1 is mapped to 4, 2 to 5, 3 to 6, 4 to 7, etc. By interchanging the first and second coordinates of each ordered pair, so here, instead of 1 mapped to 4, we say 4 is mapped to 1. Okay, 5 maps to 2, which is shown right there. And the inverse of function f is formed. It is denoted by f to the f inverse. We don't read it as f to the negative 1, but it looks like it, but we read it as f inverse. So please note that earlier 4, 5, 6, 7, that's in the set B, right? That's the range of the f. Now 4, 5, 6, 7 becomes the first coordinate of the order pairs, so it becomes the domain. So the range of the original function becomes the domain, and domain of the original function becomes the range of the inverse function. And we actually can see that the inverse is basically 4 is mapped to 1, 5 is mapped to back to 2, 6 to 3, 7 to 4. And this red mapping, we call it the F inverse. Okay. All right. And this is a graph of the inverse and the function and its inverse. So in the, say A is an element of F, elements in the domain of F, and under F it is mapped to B. Now under the inverse it is mapped back to A. So I can actually visualize this as this: A under F is mapped to B, right? So that's what it is. A is mapped to B. And then B under the F inverse is mapped back to A. So B under F inverse is mapped back to A. And similarly, if you begin with B, so B under inverse of F, it is mapped to A. So we are talking about this direction here. And then A under F is mapped to B. So we can actually see that if you begin with A, you end up with A under these two functions. So basically, when two functions are inverse and original functions, they are related in a kind of special way. The action of one undoes the action of the other. Okay, so basically you recover that. So therefore, this is actually the definition. A function g is the inverse function of f, denoted by f inverse, when f of its inverse is equal to x. So f undoes the inverse. Okay, so you recover the x. And g, which is the inverse of f, g of f is equal to x. So the inverse undoes the f. The inverse of f undoes f. Okay, so therefore their actions are cancelled basically. Now, so a couple notes: if g is the inverse of function f, then f is the inverse of function g. So they're inverse of each other. And the domain of f is the range of its inverse. The range of f is the domain of its inverse. A function need not have an inverse function, but when it does, the inverse function is unique. Now let's do some examples, okay? So here we would like to determine whether each of the following is the inverse of each other, and if so, identify the domain and range. Now, how do we identify whether they're inverse of each other? We just need to make sure that it meets the definition, right? So therefore, we have to check f of g, is that equal to x? If so, then we have to check g of f, is that equal to x? When these two are true, then we can conclude that they're inverse of each other. So now let's do the look at the first one. So basically, we just have to f of g of x, check this one. So this is a function composition, so we work inside out, right? So we plug in g of x inside and then do the substitution. So this one will be substituted into the function f. Therefore, we have 1 over x plus 2 and then plus 2. And we get 1 over x plus 4. And we can see this is not the same as x, and we really don't have to continue. And this already tells us that they're not inverse of each other. So therefore, we can conclude now, not inverse of each other. All right. Similarly, let's look at the second example. We just have to check f of g of x, right? Let's start with checking f of g of x, which is f of, and g of x is cube root of 1 minus x. And then now plug in this into function f, which is 1 minus what's cube, and this guy have to be substituted here. So it's the cube root of 1 minus x and then cube. And this is equal to 1 minus cube root, and then you raise to power 3, they kind of cancel out with each other. So you have 1 minus x, and then drop the parentheses, and the 1 cancels out. And therefore we have x. Well, that's a good sign. So f undoes the g, basically. We'll have to make sure that g undoes f, right? So we want to check g of f. We want to make sure that that's equal to x. So which is g of 1 minus x cubed. Now time for us to plug in 1 minus x cubed into function g. So cube roots of 1 minus, and what we want to plug in is 1 minus x cubed, 1 minus x cubed, and inside the root we have 1 minus 1 plus x cubed, and the 1 cancels, and therefore we have cube root of x cubed, which is x. Because both are equal to f of g of x is equal to x, g of f of x equals x. Now we can conclude they are in, so yes, f and g are inverse of each other, right? Of each other. Okay, and now let's take a look at the domain and range. In this case, this actually is a polynomial. So therefore, domain of f and range of f, and this is an odd power, odd degree. So therefore, domain and range, they're actually the same as each other, which is negative infinity to infinity. So for the f, domain is negative infinity to infinity, and range also negative infinity to infinity. For the function g, well, we already know that the range of f becomes the domain of g, which is negative infinity to infinity, and the range is the domain of f. Well, they happen to be the same here, negative infinity to infinity. Now let's check. Take a look at this function. Its domain, because this is cube root, so there's actually no restriction on the sign inside, right? So therefore it's negative infinity to infinity. And cube roots, that also when x is negative infinity, you get infinity. When x is infinity, you get negative infinity. So therefore range is negative infinity to infinity as well. All right, so we discussed the definition, and we also discussed how to verify one is inverse of each other. Now let's take a look at another property, important property. It is the reflective property of inverse functions. Let me zoom out a little bit here so that we can see the graph here as well. So this theorem says the graph of f contains the points a, b, if and only if the graph of f inverse contains the points b, a. This is pretty intuitive, because if a, b is on f, which means f of a equals b, well, the inverse, definitely f inverse of b equals a, right? So in other words, that means if AB is on f, then BA, this point is on the f inverse. This is coming from the definition. Now what that means is actually in xy plane, the points AB and BA, they are symmetric with respect to the line y equals x. So AB, point AB and BA are symmetric with respect to this identity line. So therefore, for any function f, if inverse exists, then its inverse should be symmetric with respect to the y equals x, this identity line. This is what this theorem is all about. The next theorem is the existence of an inverse theorem. So it says a function has an inverse function if and only if it is one-to-one. Okay, I feel like this probably can be seen. Let's give one example so that you can see that if it's not one-to-one, then you cannot have an inverse. For instance, I'm gonna make a little graph here. Okay, maybe somewhere here. So this is your a, this is your b, this is the function f. It maps. So I'm gonna say it maps a red dot to a star, and it also maps a square to the same star. Okay, so both are mapped to star. Obviously, this is not one-to-one, this is two-to-one. Now take a look at the other direction. If you look at the backwards direction, star is mapped back to the square, and star is also mapped back to the red dots. Well, this would not be considered as function, because to be a function, every single element can only be mapped to exactly one element on the other on the other sets, right? So here you cannot have one element is mapped to two elements on the other set. So therefore, this would not be considered. Therefore, in this case, the inverse doesn't exist. So not a rigorous proof, but this demonstrates that you have to have one-to-one function so that the function has inverse. Okay. Now second part of this theorem is saying if f is strictly monotonic on its entire domain, monotonic means either strictly increasing or strictly decreasing, then it will be one-to-one, and therefore inverse exists. Now please note that this theorem, you have to read this carefully. This says if it is monotonic, then that happens, right? It doesn't say if it's not monotonic, that won't happen. So it's possible that a function is not monotonic and it still is one-to-one, and therefore inverse exists. Now let's review the horizontal line test. The horizontal line test, this rule says a function f has inverse if there's no horizontal line that intersects the graph of the function at more than one point. That means every horizontal line you draw, it will intersect the graph one or less number of points. Okay. Let's apply this one to the following. So let's look at the first graph right there. And all we need to do is to draw a horizontal line, right? And then check how many points that it intersects. Now this time it intersects 2 points here on this graph. And that means this is not one-to-one, because when x is roughly about -2, the y value is the same as the when x is 2, they have the same y value. So therefore this is not one-to-one. Because it's not one-to-one, so no inverse, right? Inverse does not exist. So no inverse, or inverse does not exist. And the second one, if you draw a horizontal line and it intersects at most one point, and you may argue here down below it doesn't intersect at all. That's fine, because the point is the horizontal line cannot intersect more than 1 point, so 0 point is fine. So therefore this is completely okay. We say inverse exists. Okay. All right, now let's look at the next problem. Here we want to check whether each one of these is strictly monotonic on its domain, and therefore inverse exists. So there are different approaches. Because we're talking about horizontal line tests, I would use the geometrical approach, make a graph of that. So please, using your calculator, make a graph of that. And it should look like something like this. Well, this is a rough graph. By no means it's accurate. Just want to share the shape. And here this y-intercept is 2 and x-intercept is 1. So they are not on the correct scale, and just want to share the shape. And then here definitely pass the horizontal line test, right? So therefore, so pass horizontal line test. Horizontal line test. So therefore inverse exists. Of course, this is a calculus class. Definitely, I would say give a try to see, use calculus knowledge to show that this actually is strictly monotonic. Therefore, it is one-to-one, and inverse exists. For instance, we can f prime of x equals, and find the derivative of this polynomial. It is -1 minus x, actually 3x squared, right? Okay, minus 3x squared. And because x squared guarantees that this will never be negative, therefore -1 minus 3 times a never negative number, this will be always less than 0. And so that means f is strictly decreasing on its domain, and therefore it's one-to-one, and inverse exists. Now look at the part B again. Pause the video and then make a graph of it. So this will be interesting. So here again, by no means this is an accurate graph. I just want to show the general shape. And using a graphing calculator, it looks something like that, okay? Like something like that. And then you might think that, okay, this actually is one-to-one. In fact, it is not. If you zoom in the graph enough, you will see actually, let me refine this one. Here, this actually is a local minimum, and after that, it bends, it goes up a little before it drops down. So actually, there's a bump over there, okay? So because it has a relative max and relative minimum, it will not pass the horizontal line test. When you draw a line somewhere in between the max and min, it will definitely cross multiple, it will create multiple intersects, right? So therefore, this is not one-to-one. Now, of course, we can actually show that calculus-wise speaking, you can find, using the critical numbers, find and prove that there are relative maximum and relative minimum. Therefore, this is not strictly monotonic on its domain, so that it is not one-to-one. So F does not have inverse. Because the horizontal line test fails. Now, next, let's review how to find inverse function. Step number one, make sure that the function has inverse by checking whether it is strictly monotonic or one-to-one. Step two, solve for x as a function of y. And step 3, interchange x and y, then the resulting equation is the inverse. And then you want to make sure that the domain of the inverse is clearly stated when necessary. Of course, if it's very intuitive and without any misunderstanding, it's both, it's well, it's known, then you really don't have to. But if it is not that intuitive, you should clearly state the domain. And then make sure that what you found is actually the inverse by checking using the definition. All right. Actually, if you remember, sometimes in college algebra class, students are told to interchange x and y first, and then solve for y in that case, right? So it's okay either way. They will end up with the same answer, so it's not that big of a deal which order you do it. They will end up be the same. Now let's do the next example. Find the inverse of the following function. First of all, let's make sure that the inverse exists by checking it is strictly monotonic or one-to-one. We can use calculus approach, find the derivative and check the sign, right? Or we can use the geometry approach. So by the way, do a little work for you here. This y equals square root of 4 minus x squared. If you square both sides, y squared equals 4 minus x squared. And move the x squared over, you get x squared plus y squared equals 4. Hopefully you recognize what this is. This actually is a circle with radius 2, right? Of course, because what you begin with, square root of something that's non-negative, so it's representing the top half of the circle. Now, time for us to take a look at the domain here. The domain says x is from 0 to 2, including the boundary point. So therefore, actually, the red piece is what this function is. So obviously, the horizontal line test shows that this is a one-to-one function, right? Therefore, inverse exists. Now, step number 2, let's solve for x. Okay. By the way, we should clearly state that because this is one-to-one, by the way, it is decreasing. Therefore, we can find the range quickly. So when x is 0, right, the y is square root of 4, which is 2. When x is 2, y is actually 0. So the domain is 0 to 2, including both values. The reason we know the domain is 0 to 2 is not because of the boundary points corresponding to 2 and 0. It's strictly decreasing. So therefore we know here this is the max, this is the min, so all the values in between, that's in the domain. So again, because of its monotonic, therefore domain is from 0 to 2. Now next, solve for x, right? We already did some algebra there, right? So we square both sides, and then we move x over, and then we subtract y squared to both sides, and finally we take the square roots, right? So when we take the square roots, you have to be careful. You have to consider the sign. Is that positive or minus? You have to consider the sign here. Now, let's time to take a look at which value that we are gonna take. So we have not swapped interchange x and y yet. So therefore, this x is still the same as this x, right? And this x is in between 0 to 2 inclusive, and they are all non-negative values. So therefore, I will keep the positive sign right there, and then you should ignore, right? I'm gonna make a note, ignore the other one for that reason. Now finally, the last step is to interchange x and y. So therefore, y equals square root of 4 minus x. This is the inverse, okay? To get the inverse. Now this inverse, the x is, the domain of this inverse should be the range. Oops, I'm sorry, actually, earlier, this should be the range, right? Because we are given the domain, we talked about the range. So apologize for that. This actually supposed to be the range. So the range of the original function becomes the domain of the inverse. So therefore, the domain is actually x greater than or equal to 0, less than or equal to 2. And oftentimes, we write it as f inverse of x equals square root of 4 minus x. Okay, that's usually what we write at the end. And of course, with the domain for that. Now, feel free to check using the very last, using the definition as the last step. Well, I'm going to skip that because I know it actually is its inverse. By the way, now time for you to compare its inverse and the original function. Do you see that they are actually identical? Hopefully, you are not surprised because this is what we are looking at is the part of the circle in the first quadrant, and it's definitely symmetrical with respect to the identity line y equals x, right? So therefore, itself is symmetrical with respect to this identity line. Therefore, itself is the inverse. All right, so this is the problem number 4. We are gonna do one more problem in this review. So this problem is we're gonna consider function sine x. Show that it is not one-to-one on the entire real number line. This is pretty easy to show because you just need to provide some counterexamples so that it is not one-to-one, right? And then there are so many examples, just name a few. For instance, sine of 0 is equal to sine of pi, and they're both equal to 0. So there are two x values corresponding to the same y value. You know this is not one-to-one. This will be sufficient. So it is not one-to-one. Okay, just use one counterexample. Now next, let's show that in this interval, this is the largest interval centered at the origin on which f is strictly monotonic. Well, first of all, when we want to show that it's monotonic, which either increasing or decreasing, the first derivative is usually a good, look at the sign of the first derivative, right? So f prime of x is cosine x. Cosine x is strictly greater than 0 on this interval, negative pi over 2 to pi over 2. It is actually equal to 0 at these 2 points, 2 boundary points. But from here we can see that it's strictly increasing inside the interval. Okay, and now how do we handle the boundary points? So because since sine x is continuous function, right? Continuous function. And sine at these two endpoints achieves its relative minimum and maximum. So it's continuous function and attains its relative minimum and relative max at the boundary points at x equals negative pi over 2 and x equals pi over 2 with respectively. So we can actually conclude it's continuous, therefore it's connected. So we can conclude sine x is strictly increasing on this closed interval. Okay. Therefore, any larger interval will not be strictly monotonic because this is the relative max. When you go beyond to the left these points, it will not be. So basically, this is what I meant. Okay. Suppose this is negative pi over 2. Because this is relative minimum, so if you move further to the left, it will be, the value will be higher than this minimum. And when that happens, the horizontal line will fail, right? So that's why we can claim that any larger interval will not be strictly increasing. Now finally, we're going to talk about the derivatives of inverse function. Let's begin with some statements, and this is a theorem, the continuity and differentiability of inverse functions. Say f is a function whose domain is an interval I, and f has an inverse function, then the following is true. If f is continuous on its domain, then so is f inverse on its domain. If f is increasing on its domain, then so is f inverse on its domain. If f is decreasing, then f inverse is also decreasing. If f is differentiable on an interval containing c, and f prime of c is not equal to 0, then f inverse is differentiable at f of c. Before we introduce the formula for the derivative of inverse, let's look at this example. Okay. So consider these two functions, x cubed and x to the 1/3. By the way, x to the 1/3 is actually cube root of x. And you can quickly show that they're actually inverse of each other, right? So this is cube, this is the cube roots, one undoes the other. Let's find the derivative of f of x at the following points. So f prime of x is 3x squared. And when x is 1, this is going to be, so f prime of 1 is just plugging 1 into this derivative, which is 3 times 1 squared, which is 3. Now, f prime of 2 will be 3 times 2 squared, right? Which is 12. And f prime of 3 is equal to 3 times 3 squared, which is 27. And f prime of 0, which is 3 times 0, which is 0. Okay, time for us to take a look at the derivative of the inverse. It's inverse, g of x. Now the derivative using the power rule, pull the 1/3 out, 1/3 times x to the 1/3 minus 1, which is 1 over cube root of x squared. Now let's find the derivative of the inverse, at the following points. So the first one is, when x is 1, y is 1. So therefore, when x is 1, y is 1 for the inverse as well. So g prime of 1 is equal to 1 over 3 times, well, when you plug in 1 square is 1, and a cube root, which is still 1, right? So therefore, which is 1/3. And let's find the inverse. Original function, when x is 2, the y is 8. So here in the inverse, when x is 8, y is 2. You have to change x and y, right? They swap. Now, g prime of 8, by the way, this 8 is the f of 2. 8 is f of 2, equals 1 over 3 times cube root of, actually I would prefer to cube root of 8 and then square. You can do that, okay? You can do that. Which is 1 over 3 times the cube root of 8 is 2, so 2 square. So times 2 square, which is 1 over 12, right? 3 times 2 square. This is 3 times 2 square. And continue to the next one. Let me zoom in a little. G prime of 27. G prime of 27. And here, when x is 3, y is 27. For the inverse, when x is 27, y is 3. It maps the 27 backwards back to 3. So this is equal to 1 over 3 times cube root of 27 square which is 1 over 3 times 3 square, which is identical to this guy, right? So 1 over 27. Lastly, g prime of 0, which is 1 over 3 times 0, which is undefined. Okay, time for you to observe the relationship, the derivative of the original function and the derivative of the inverse. So this is 3, this is 1 over 3. This is 12, this is 1 over 12. 27, 1 over 27. 0, 1 over 0 is undefined, right? So your observation, hopefully you can see that this value is actually reciprocal of that. So this actually is the next theorem. Okay, this is what the next theorem is saying. This theorem says f is invertible and differentiable on interval I if f has an inverse g. So here g is the inverse of f. Then g is differentiable at any x for which f prime of g of x is not equal to 0. In other words, f prime of this f inverse of x is not equal to 0. Basically, this cannot be 0. Okay, this cannot be 0. Otherwise, it's the derivative will not exist. And here's the result. G prime of x, keep in mind g is the inverse. I prefer this version actually. So g prime of x equals 1 over f prime of g of x. Basically, the derivative of inverse is the reciprocal of the derivative of the original function. That's what we are saying. However, this has to be, you have to be a little careful here, okay? This x, this is the inverse. This x is actually the y value of the original function. Okay, just like here, these x values, they are the y value of the original function. So therefore, this g of x represents, so g of x, like g of this x, the y value of the inverse function is actually x value of the original function. So therefore, this is saying g prime of x is 1 over f prime of the value. This value, okay, should be equal to g of x. Now, this is something I would prefer to use. So I would prefer f inverse, the derivative of f inverse is equal to, f inverse of x is equal to 1 over the derivative of f at f inverse of x. Now, by the way, this reciprocal relationship is sometimes written in Leibniz notation as dy dx equals 1 over dx dy. So they are just actually dx dy, that's the inverse of the y, right? Okay, x is the inverse of the y. All right, let's apply this result, okay? Let's apply this result. Here, f of x is equal to this guy, square root of x plus x squared plus 1, where x is greater than or equal to 0. This actually is monotonic, strictly increasing, because each one of those is like these functions, they are strictly increasing, and therefore this whole function is strictly increasing. Please note that f of 1 is 3, so when you plug in 1 here, the y value is 3. Now let's find f inverse of 3. What is f inverse of 3? So because f of 1 is 3, so therefore f inverse of 3 is equal to 1, right? That's the inverse. Now let's find the derivative of the f inverse at 3. According to the theorem we just introduced, and this is equal to 1 over f prime of f inverse of 3. And this is equal to, well, by the way, what is f inverse of 3? it is the x value, so the f of this value is equal to 3, right? So that's the 1. So f of 1 is equal to 3. So this will be the x value for the original function. So this will be f prime of the 1. Now, do you see that we actually find the derivative of f inverse without finding the f inverse? We can just take advantage of the derivative of the original function f. And in fact, if you want to find the inverse of this function, can you give a try? And if you give a try, then you can see it's very, very difficult, right? And on top of my head, I don't even know how to find the inverse of this function. However, we don't need the inverse. We're still able to find the derivative of the inverse. So now time for us to find the f prime, okay? So f prime of x, let's find the derivative of this guy. The derivative of square root of x is 1 over 2 square root of x. Please verify that. You can use the power rule. Think of this as x to the 1/2 and find the derivative, which is this guy, right? And it gives you that. Plus the derivative of x squared is 2x. So therefore, f prime of 1 is equal to 1 over 2 times square root of 1 plus 2 times 1, which is 1 over 2 plus 2. So therefore, and by the way, this is 5 over 2. So therefore, this is 1 over the 5 over 2, which is 2/5. All right, so that's the example. We use the rule directly, and then we find the derivative of f, and then use it to find the derivative of the inverse. Now let's close this section by actually using the table provided to find the derivative of the following. So now, let's look at the first one. The derivative of f inverse at 0. Okay, according to the theorem, this is equal to 1 over f prime of f inverse of 0. Okay, we need to figure out the x value so that f of this value is equal to 0. So therefore, let's look at the so the y f inverse of 0, that means when the y is 0, what is its x value, right? So therefore, this is equal to 1 over f prime. So f inverse of 0 is, we're going to find the inverse, which is -4. So -4. And f prime of -4 is equal to 5. This is equal to 1 over 5. Pause the video and then try the next one. Give yourself a little room to think about it. Now, for the next one, it's going to be 1 over f prime of k. So we need to figure out what x value, so that f of x is equal to 1, right? So f inverse of 1. F inverse of 1. And f inverse of 1, so will be 2. The x value is, -2. F of -2 is equal to 1. So f inverse of 1 is -2. This is -2. And this will be 1 over the derivative of f at -2 is 4. So this is 1/4. The next one actually is easier than the first two because f of 4 is given there, and I know this is 1 over f prime of, I know this answer is going to be 4 right there. This is the 4. Now let me convince you that, okay? Let me convince you that according to the theorem, inside this will be f inverse of this guy, right? So f inverse of this guy, just like here, when this is earlier, when this is 1, this is going to be f inverse of the 1. When this is 0, here this is f inverse of the 0. You want to find x value so that its y value is 0. You want to find x value so that y value is 1. So now here, inside here, you want to find x value so that its y value is f of 4. Isn't that the x value is 4? But I'm going to still follow the whole theorem, show you that actually it's easier. So inside should be f inverse of this guy, right? So f of 4. And what is f inverse of f4, which is 4? You just f inverse undoes f. So therefore f prime of 4. And this is equal to, and by the way, this 4 is actually that 4. So this is 1 over 1, which is 1. Now similarly, the very last one will be 1 over f prime of the 2, okay, the 2. And if you get lost here, I'm going to convince you here by using the theorem directly. So f inverse, and inside, I'm sorry, this is f prime, not f inverse. F prime of f inverse of this guy, of this guy, right? F of 2. And f inverse of f of 2, this guy undoes the other, so it's going to be 2. So this is actually 1 over f prime of 2, okay, which is this guy. So basically, this is the, here this is the x value so that its y value is shown here, okay. And then this is equal to 1 over, and then we can look up the f of 2. f of 2, when this is x is 2, f prime of 2 is 2. So 1 over 2. All right, this is it for this section.